G'day, in this video, we're going to be using Newton's second law of motion specifically to really begin to bridge the gap between kinematics and dynamics. This video's focus is on dot point 2.2.2, Module 2 dynamics, continuing with the second inquiry question, which is how can the motion of objects be explained and analysed? The content statement for this one is quite broad. It says that we need to investigate, describe, and analyse the acceleration of a single object subjected to constant net force and relate the motion of the object to Newton's second law of motion. So the general gist of this here is the idea that because we have F equals ma as the equation that is quite representative of what's included in Newton's second law of motion, that if we have the kinematic measurement of acceleration, we can either find the net force and complete dynamics calculations, or vice versa. If we know information about the force that's being applied to an object, we can use Newton's second law of motion to find acceleration and then hopefully be able to calculate some other kinematic aspects. Just to note as well, the dot point requires us to focus on this relationship in Newton's second law using a variety of methods. So the main focus of this video in particular is to look at kinematic data and determine applied and frictional forces from it. So it's going to build on an activity that I did with motion on an inclined plane and the practical work that you've done previously, but bringing in some of those friction concepts into the mix. And I will also just really quickly at the beginning introduce a couple of PhET simulations that we'll be using in class to explore the second law in a little bit more detail. So these are the links to those PhET simulations. I'm not going to go through them with you right now in this video, but it will be a point of discussion that we will have for at least one lesson coming up soon. So these simulations are all about forces of motion. You can change up the friction, you can change up the angles of the incline, and we'll just kind of play around with some of those simulations to see how Newton's laws of motion can be applied to some simple dynamic scenarios. But the main part of today's lesson is looking at being able to calculate frictional coefficients on an inclined plane just using some very basic kinematic data. As you can see in the question, it's quite slim. There's not a lot of data that we've been given. However, with simply just this kinematic data here, so the displacement and the time, we should be able to have enough information to complete some calculations and find the coefficient of kinetic friction of an object. So here it just says we have a 2 kilo block. It's placed on an incline of 17 degrees. And with this kinematic data, we should again be able to find the coefficient of kinetic friction. Let's get straight into that solution. So for this question, we've been told that a 2 kilo block is placed on an incline of 17 degrees and that we need to calculate the coefficient of kinetic friction if the block travels 0.25 meters in 0.54 seconds. Now to get this question started, I've already drawn up a diagram showing some of the relevant information, the mass of the block as well as the incline of the plane. And I've also gone and drawn in all of the relevant forces that we'll need to focus on when coming up with a solution for this question. There are 3 forces to look at which are parallel to the incline. The first one here is the applied force. We also have the net force, and we have the force of kinetic friction, all of which are quite closely interrelated. The applied force that we have here is all of the force that is on the block pushing it down the incline, all due to the force of gravity. Because there's no other applied force in the scenario pushing the block forward, the only thing that's going to be causing it to move down the incline is the force of gravity. However, not all of the applied force is going to lead to an acceleration. Some of it is reduced by kinetic friction, meaning that this net force here is going to be the sum of that applied force and kinetic force. I've also drawn in the normal force, which will be required a little later on in the solution. So let's start by reflecting on how we can actually come to solving this problem. We're being asked here to calculate the coefficient of kinetic friction. In other words, we're being asked to find mu k. Now there's one equation that we've already been looking at which allows us to calculate for mu k, and that is that the force of kinetic friction is equal to mu k times the normal force. In other words, if we know the force of kinetic friction and the normal force in this scenario, we can rearrange the equation to calculate for mu k. So what we need to do is develop a little bit of a strategy to be able to calculate for that kinetic friction. And the simplest way is to reflect on its relationship to the applied force and the net force. So there is a relationship between all of those things. As usual, the net force that is being applied to an object is just the sum of all of the other forces. So in this situation, that would be the applied force added on to the kinetic force of friction. So here in this situation, we can calculate for kinetic friction if we know the net force and the applied force, both of which we'll need to calculate separately. Essentially, this is going to mean there are two key parts to our solution. The first thing that we need to be able to do is use our kinematic data that we have to find the net force. And we'll also need to do some vector analysis to find our applied force. Let's start with the net force to begin with. So for this part of the problem, what I'm going to be doing is using the F equals ma equation to be able to convert here our kinematic data in the form of A to an actual force. Here we have to kind of work the problem backwards a little bit because this net force here, F net, is going to be causing the acceleration in the block. Now we have a little bit of data here, again, the displacement and the time, which should enable us to be able to find this acceleration. Once we know the acceleration, we can then find what force is being applied to cause that motion. So to begin with, I'm going to construct a little bit of a mini data column. So far, the data that we have, which is relevant, is S, which is equal to 0.25 meters. We have T, which is equal to 0.54 seconds, and M, which is equal to 2 kilos. Now at this point, we have 3 kinematic variables at play, but we know from our kinematic equations that they all have 4 variables. The current variables that we have missing are V and U, the final and initial velocity. We only need to know one of them. And actually for this question, the value for U is given in the question, it's just a little bit discrete. It is implied in this question that because the 2 kilo block was placed on the incline, that before it was released and let go, its initial velocity U was 0. And we need to work with this assumption to actually allow our calculation to move forward. So here we can assume that U is equal to 0 meters per second. Now that we have 4 different kinematic values, A, S, T, and U, we're able to essentially select and apply a kinematic equation here to calculate for A. The equation that we need to use is that S is equal to UT plus a half AT squared. Now to solve for A, what we will need to do is rearrange our equation for A and make it the subject. So the first thing that I'm going to do here is subtract UT. So S minus UT is equal to half AT squared. The next step, I'm going to multiply up the 2 in the half and divide down the t squared, which means that we're going to end up with A is equal to 2 times S minus UT divided by t squared. From here, we can substitute and solve for A. So that's going to be equal to 2 times 0.25 minus 0 times 0.54. Something to note here is this entire term with U in it is going to cancel out because U is equal to 0. Then we can divide all of that by t squared, so 0.54 square. To simplify all of that out, 2 times 0.25 is 0.5 divided by 0.54 squared. And the number that we should get is something in the ballpark of 1.71 meters per second squared. And that here is the acceleration of the block as it moves down the incline. With that data, we now have the mass of the object and the acceleration. So the mass is 2 kilos and the acceleration is 1.71 meters per second squared. And that means at this point we can substitute into our F equals ma formula, and that will give us the net force that is being applied on the block. So F net is equal to 2 times 1.71, and that is equal to 3.43 newtons, or thereabouts. So with that first calculation, we now have our net force, which we gained through using our kinematic data, which means that we are one step closer to being able to calculate the force of kinetic friction. The only thing that is currently missing is this applied force. And as I said before, we will need to do some vector analysis to be able to find it. So the first thing that I've done for our vector analysis is put in a slightly more simplified diagram that removes all of the forces which are parallel to the incline. Here we're just focusing on Fg and the normal force. As I stated earlier, the applied force which is being placed on the block is simply coming from the force of gravity. However, that applied force is not equal to the force of gravity because the only direction that that force can go in essentially is in the direction parallel to the incline. What that essentially means is, in this problem, it makes sense to break up our FG vector into two perpendicular components. Now, they won't be in the x and y axis like we've done in previous questions. Instead, the vector here at the bottom is going to be parallel to the incline. And this vector here is actually going to be the force applied due to gravity. The other vector here is going to be perpendicular and is actually equal but in opposite directions to the normal force. I'll draw that up in a second diagram to show you what that roughly looks like. So the downward force here is still Fg. Something to note as well is we can calculate that quite easily by simply doing Fg is equal to mg, the mass of the object times the acceleration due to gravity. So just a reinterpretation of Newton's second law, F equals ma. But we also have here F, what we call perpendicular, and F parallel. Now, these two vectors are very similar to what we would usually call Fx and Fy, two forces in perpendicular components or in the x and y axis. However, we can clearly see that these two vectors are not in the x and y axis. However, they are still perpendicular to each other and form a right angled triangle with our hypotenuse here, Fg. So we can still do a lot of the same trigonometry that we're used to doing here in this kind of context. But because we're working on an inclined plane, what would usually be our x and y components are no longer in line with the x and y axis. So some things just to keep in mind when we draw something up like this in an inclined plane sort of scenario. First off is that F perpendicular is equal and opposite to the normal force, and that just comes from Newton's third law. This perpendicular force is just essentially the block pushing into the plane. But then this F parallel force that we have is equal to our applied force. So here, this vector accounts for all of the force that is being applied to the block parallel to the incline. So in other words, the force which is actually going to cause some amount of movement in the block. So in other words, the component of the gravity force which is actually going to cause movement in the block parallel to the incline. So to figure out what this applied force is, we are going to have to do some right angled trigonometry. Calculating Fg is quite easy. That's just 2 kilos times the acceleration due to gravity, which is 9.8. And that is equal to 19.6 newtons. Even though we have Fg, we can't use a simple rule like Pythagoras to find the parallel force because we don't have any information about the perpendicular force yet. What that's going to mean is that we are going to have to do some right angled trigonometry. So either a SOHCAHTOA or a TOA. And in order to do that, we're going to need to know one of the non-right angled on the triangle itself. Easiest way to figure that out for a question like this is to look at the angle at the bottom that includes the parallel vector here. Something that I'm just going to point out is that because this vector at the bottom is parallel to the inclined plane, this angle here is going to be exactly the same as that incline. In other words, this is 17 degrees. Now, if this is 17 degrees, that's actually going to give us enough information to find this internal angle in the triangle. What we need to keep in mind or take into account is that this dotted line here, which we would assume is a flat surface like a table or the floor, is always going to be perpendicular to Fg, meaning that this angle here is right angled as well, meaning that 17 degrees plus this internal angle adds up to 90. And if that's the case, then the angle inside the triangle here is 73 degrees. So now that we have the force of gravity, Fg, the hypotenuse of this right angled triangle, and our 73 degrees here, we have enough information to be able to find our parallel side. We're also going to be able to use it to find the perpendicular side a little bit later when we need it. So when we're completing our right angled trig and using this angle here, we're going to need to use the adjacent side and the hypotenuse. If that's the case, then we need to be working with cos. And cos theta is equal to the adjacent side divided by the hypotenuse. Summing in what we know, that means that cos of 73 is going to be equal to our F parallel, which is also our applied force here, divided by the hypotenuse, which is 19.6. We can then rearrange to solve for the parallel force by multiplying up 19.6. So F parallel is equal to 19.6 times cos of 73. And that is equal to about 5.73 newtons. And as we said before, this is the applied force which is being placed onto the block. So at this point, we have the net force and the applied force, which gives us all the information that we need to calculate the force of kinetic friction. So if I were to rearrange that equation, kinetic friction force will be equal to the net force minus the applied force. So that will be 3.43 newtons minus 5.73, which is equal to negative 2.3 newtons. In other words, it's 2.3 newtons, but in the opposite direction to the net and applied force. And that information there gets us a lot closer to being able to calculate what we were asked to find at the beginning of the question, the coefficient of kinetic friction, so mu k. So we currently have the force of kinetic friction, but what is missing is the magnitude of the normal force. As we identified earlier, the perpendicular force is going to be equal but opposite in direction to the normal force. When we're using our friction equation up here, we don't have to worry that much about the direction of any of these forces. So in other words, really, the magnitude of the perpendicular force is equal to the magnitude of the normal force. So if we're able to calculate this one here, F perpendicular, that should then allow us to substitute that value in for the normal force and solve for mu k. Now at this point, you could either use Pythagoras' theorem to figure out what the perpendicular force is. I'm going to use some right-angled trig. To calculate for F parallel, which is currently opposite to the angle that we have in our right-angled triangle, we're going to have to use sine. In other words, our opposite side and our hypotenuse will be substituted into the equation. And that value comes to about 18.74 newtons of force. And remember, as we said before, that because the perpendicular force is equal but opposite to the normal force, if we're not reporting any directions here and we're just looking at magnitude, not the vector itself, we can say that here the normal force is also equal to 18.74 newtons. So to finish off our solution, now that we have the kinetic force of friction, which is here 2.3 newtons, the negative sign is not going to need to get substituted in here because we're not concerned about direction, just magnitude. And because we also have the normal force here, 18.74 newtons, we can now rearrange our equation, substitute in, and solve for the coefficient of kinetic friction in this scenario. So first off, mu k is going to be equal to the force of kinetic friction divided by the normal force. That's going to mean that we're going to do 2.3 divided by 18.74. And that's going to be equal to about 0.123. Now, when we look at the original question and the data that we used in this problem, the mass of the block has only been reported to one significant figures here, 2 kilos, which is going to mean that we need to round our final answer to one significant figure as well. So the final thing that I'm going to write here is that mu k is equal to 0.1, and that's to one significant figure. And that here is going to be our final answer. So quite a long and complex problem, but we're integrating now our kinematics, our trigonometry, as well as some of our force equations that we've been working with to be able to calculate for the coefficient of static friction, just given a small amount of kinematic data. Thank you very much, everyone. In the next video, we're going to be connecting this concept of force to the ideas of work and energy, and also look at energy changes in scenarios where gravity is the dominant force. But until then, have a good one.